Good morning, students. Today, the topic of our discussion is boundary conditions. First of all, what is boundary condition? Boundary means whose boundary? Boundary means suppose there is a field and the field lies in a region, that region consisting of two different mediums, and the field is passing from one medium to another medium. The two mediums can be anything. It may be two different dielectric of different dielectric constant. Let it be eta 1 and eta 2. The two medium could be free space and dielectric. One is free space, another is some other dielectric. The third case could be a conductor and a free space. One medium is a conductor, another medium is free space. So if such field exists, and between any two medium, then what are the conditions the field should satisfy at the interface, that is at the boundary? This is the electric field flowing from this medium to this medium, means electric field is present in a place where there are two medium. So what are the conditions E should satisfy at this boundary? That is called boundary conditions. Okay, so one thing we have to remember, that electric field, first of all we have to take its two component. One is tangential component, another one is normal component. We will find the expression individually, first for tangential component and second for normal component. Not only for E, that is electric field intensity, we will find expression for electric flux density D also. For all these conditions, if we find out the conditions for dielectric, it would be easy to find out the other two. Okay, so let us start with the dielectric boundary. That is, one medium is a dielectric, another medium is also a dielectric of dielectric constant eta 2. Okay, now as I have said that we will consider two things, tangential component of electric field and electric flux density, and normal component of electric field and electric field flux density individually. Okay, so first of all let us take the tangential component. Okay, so for this let us consider that this is a boundary. This is the boundary. Okay, and here above the boundary there is a medium whose dielectric constant is ER1. Okay, and dielectric, what we call it, relative permittivity, and below it there is a medium whose relative permittivity is ER2. Let it be medium 1 and this is medium 2. Okay, now I am considering only the tangential component of electric field. Okay, let the tangential component are ET1 and ET2. Okay, so this will be like this. I am writing is ET1. Okay, and here it is ET2. Tangential component of the electric field in medium 1, tangential component of the electric field in medium 2. Okay, now for getting the expression I have to consider one closed loop, one closed path. Okay, suppose this is the closed path. Okay, let us give it the name A, B, C and D. Okay, now let the direction is from A to B, then B to C, C to D and D to A. One is moving from A to and back to A, B, C and back to A. Okay, so what we can do, we can apply Maxwell's second equation. So as per Maxwell's second equation, what is Maxwell's second equation? That in a closed loop the potential is 0 and potential is what? E dot dl. Therefore, in a closed loop, E dot dl is equal to 0. Where if when you find the closed loop integral, you will get this length a, b, c, d. Okay, let the length of AB is del x, and here also CD is del x, and here it is del y, a to d, and b to c, the length is also del y. Okay, so if it is so, we can write that from A to B, E dot dl plus B to C, E dot dl plus C to D, E dot dl plus D to A, E dot dl is equal to 0. Okay, now here from A to B, it is, as we can see, A to B, it is ET1. So I can write is ET1 into dl. Here ET1 dl is del x, so I can write del x. Now here along C to B, or B to C, sorry, B to C, there is no electric field, as we have considered only the tangential component. So along B to C and along D to A, there is no electric field, so here it will be 0. Okay, again from C to D, the direction of the path and the direction of the electric field are different, so I am writing is minus. Okay, here I will write what, ET2, and the distance is del x. Again this side there is no electric field, so this is equal to 0. So what we have got is ET1 is equal to ET2. It means the tangential component of the electric field is continuous along the boundary. So tangential component of electric field is continuous along or across the boundary. Okay, now we can write ET1 as DT1 divided by epsilon R1, and this can be written as DT2 by epsilon R2, as we know the relation between E and D. So D, that is flux density, is not continuous. Electric flux density is discontinuous at the interface, but electric field intensity is continuous at the interface. Okay, thank you.